when they start designing visualizations. And color when they start designing visualizations. And color makes visualizations attractive, eye-catchy, even memorable and beautiful. But as a visualization designer, you want to understand how to use color and what problems to avoid for effective communication. Because in the end, a beautiful visualization that is not effective is meaningless. So in today's lecture, we're going to cover how to use color in visualization. What is color? What color it means for visualization? What color scales exist that you can use to represent your data? We have 3 different scales that we're going to talk about, and we're going to talk about fallacies with color, such as the rainbow map, and how to support people with color blindness in reading your visualization correctly. Now, first of all, we want to ask the question, what is color? In the very basic terms, color is just electromagnetic radiation that hits the retina. However, the retina is only sensitive to electromagnetic radiation between 400 nanometers and 700 nanometers, and this is what we call the visible light. Everything else is ultraviolet radiation, infrared radiation, radio waves, gamma waves, and so on. So once these radiation hits our retina, it gets perceived by 2 types of cells, which are cone cells and rod cells. So rod cells are sensitive to differences in lightness, so dark or brightness, and cone cells are sensitive to specific types of color. 3 types of color, to be specific. We have cone cells that are sensitive to the blue parts of the light. We have cone cells that are sensitive to the red parts of the light, and we have cone cells that are sensitive to the green parts of light. In total, we have 120 million rods and only 6 million cones, which means that we are more sensitive to changes in lightness and darkness than to any changes in color. Here's a frequency diagram that shows which cones are sensitive to which spectrum of the light. So we have the blue cones are most sensitive for lights in 450 nanometers wavelength, and the green and red cones are closer to each other with sort of 50-50 nanometers, and the red cones with about 620 nanometers. And the rods, we can see, almost span the entire spectrum of light. Now, this is how the retina understands, and this is how the retina then forwards this information to our brain. However, from school, we know, and probably from art classes, we know different types of color models. We have only red, blue, and yellow. If we mix red and blue, we get a magenta tone. If we mix red and yellow, we get an orange tone, and red and blue makes green. Now, if we put all these colors together, we get a very dark, super color pigments, which is sort of brownish or black, and that's called the red, yellow, and blue model. There's a similar one that we use, and this is the prominent color model for painting, for drawing. And there is a similar one which is used in printing, which is made out of cyan, magenta, yellow, and black. This is just the way how the printing industry and printing machines work. So these 2 models have in common that they're called the subtractive models, because each pigment that you put on a white paper filters out light. So if you put a red dot, it removes all wavelength except blue. So only it is transparent for only blue wavelengths and would reflect only blue wavelengths. Everything else gets absorbed. So of course, if you add more of these pigments, then eventually no light will be reflected from the surface. So you get the black tone. However, this is not how the eye really works, because in our eye, as we just learned, we have rods for red, blue, and green. So if red cones and green cones are sensing at the same time, we get a yellow tone. If green cones and blue cones are sensing at the same time, we get a cyan tone. And red and blue makes magenta. Now, if all three cones are sensing at the same time or sensing the same intensity of their specific spectrum in the light, we get a white tone. And this is called an additive model. This is how televisions and how your computer screen works. However, color is more than just red, green, blue, magenta, and so on. A color value has also a luminance value, which is how bright or dark that specific color is. Color value has also a saturation value, that is how pure or how clear a color is. And the saturation ranges from a gray, which is a very low saturation, to a very pure and clear high saturation, high saturated color. And what we usually, common language, describe as color is really called hue in technical terms. So here we have the different frequencies of light, basically. Now, taking these three characteristics, luminance, saturation, and hue, into one model, into one specific understanding of color, we can create color spaces. The most common color space for data visualization is probably the HSB model, which stands for hue, saturation, and brightness, and has exactly these three values in one model. So each color that we can perceive, understand, or use in visualization corresponds to one point in this space. We have the brightness dimension, we have the saturation dimension, and we have hue. So hue is basically an angle, understand color. Now every point that we can see in color corresponds to one point in this space. We can assign each color a brightness value, a saturation value, and a hue value. And this is what you can get in common tools. This is a tool called HSB Color Picker, where you can choose a hue on the one side. You can then choose its saturation and its brightness value. And on the very right side, it gives you these values in the HSL model as a combination of the three, or as RGB value or hex if you're working on the web. So how do we use color in data visualization? Color is one of Bertin's visual variables. It's also called a retinal variable. It's one of the most prominent variables, probably. And he calls this in his model hue, because it's really about the frequency. If you look to the left of hue, we have value, which is kind of brightness, and we just heard that color is really a combination of value, hue, and saturation. So even saturation eventually can be a retinal visual variable. So color is a great visual variable. It is selective. That is, we can discriminate two different values, like in this example on the top. We see nicely the difference between the black elements and the other colored elements. It is associative, which means that we can understand or can perceive elements that have the same color quickly. It is not really quantitative. So color is not a quantitative variable, which means that you cannot assess or assign a mathematical linear value to a specific color value. You cannot do mathematics with color, in a sense. Color is also not ordered, though you could come up with an order and saying, this is my rainbow color map. This is the order of colors that say appear in the rainbow and in the spectrum of light. In fact, this is not a good order for visualization. We hear about more examples of why this is not a good choice later in this lecture. How many values can we perceive in color? Well, we can perceive theoretically many different values. However, practically, this perception is limited to comparing different colors and understanding specific colors in a visualization. So try not to use more than about 7 colors in one visualization. In experiments by Stu Card and Jock McKinley, they have investigated how well color fits to represent specific data types. So if you have quantitative data, which is really data you can do mathematics with, color is a rather poor choice. It's way poorer than using, for example, position or length to show your specific values. That's why we use bar charts to show changes in quantities rather than color use. However, if you have ordinary data, for example, shirt sizes, where you can establish an order between your data elements, color is a little bit better. It's still worse than position and color saturation, for example. Again, we're going to see more examples of why this might be an option, but it's not really the best choice. But, however, the best choice for color, the best use for color is if you have nominal data. Nominal data is the data where you have no implicit ordering between your elements, such as nations or car models or something like that, because we perceive usually color as distinctive values, and that's a good choice to show values or data that is not really ordered. Let's have a look at the color scales, because there might be some exceptions to what I've just said. Now, in visualizations, we know three main color scales. One type of color scale is the diverging color scale, where we map values from one end of the spectrum through some sort of a middle value like a 0 to a very high value on the other side. These ones you see on the left. In the middle we have sequential color scales, which go from one value gradually to another one. And we have qualitative color scale, which are made for representing nominal data and which are perceptually optimized so that none of the colors is closer to any other color than it must be. So the distance, the perceptual distance between each of the colors is the same, in order to not imply any specific ordering in these colors. You can, of course, then combine all these colors, all these color scales into more complicated color scales. So if you have a diverging and a sequential data, like in the center of this schema, then you have the specific combinations, and you can combine many different types of color, many different types of data to create color. Some of them are more easier to read than others. For example, this diverging versus diverging is sometimes a little bit hard to understand. I would try to avoid this and using instead other visual variables, for example. There's a good tool online that helps you choosing color scales, which I'm going to demonstrate just now. Colorbrewer.org is very simple. If you want a sequential data set in a sequential color scale, you click on this button here and it gives you a set of color scales, which you then can see how does it work out in this map on the right, for example. You can also choose a number of classes. If you just want to have 3 classes, then here's a good choice, and you get these values in hex values so that you can export them. If you want a diverging color scale, it's the same here. Let's increase the values. If you like this one the most, again, you see all the values you can export, and the same for qualitative data sets. Now, most interesting are really these qualitative data sets, color scales, because that's the one that are most tricky to create and most tricky to use. So here you have a set of qualitative color scales on this map, some using more saturated colors, others use lighter colors. That depends a little bit on your specific application, on what other sort of information you want to show, potentially on the output medium, if this is a print or if this is on a mobile phone, whatever you want to really do. Now, Colorbrewer is also great because it allows you to go into the colorblind safe mode, which leaves you only those scales that are colorblind safe, and we see for this qualitative scales that we had, none of them is really colorblind safe. Now, I don't want to tell too much about color blindness at this point. We're going to talk about it a bit later because it's a very complicated um, topic. But if you reduce the number of classes, you can come to a color scale that is eventually colorblind safe, and you're going to see the same across all the others. Divergent colors, for example, which scales are colorblind safe and which ones are not. So play around with Color Brewer is really great. It has been developed by vision psychologists. The scales that they provide are based on research.